Okay, so today we're going to try to solve Navier Stokes equation for Couette flow. So flow between two parallel plates, and we're going to try to do this as general as possible so that we can sort of apply the results to as many different, things as possible. So just so you know what we're looking at, we sort of have two plates parallel like this at some sort of angle. This extends indefinitely in either direction, and we have some sort of fluid running along this direction. So I'm going to have gravity acting downward, and we'll call this distance across the plates, we'll call this L. So the first thing we want to do is we want to define some sort of coordinate system. The most versatile coordinate system we can use is simply going to be along the incline. So at this point you typically use X, Y, or Z. I want to keep this as general as possible, so we're just going to call this the parallel coordinate and the perpendicular coordinate. Okay? So before we start solving these problems, it's good to have a couple of assumptions that we could use to simplify a lot of our calculations later. So the assumptions that we're going to use are going to be as follows. First, we're going to assume that the system is at some sort of steady state. And what this means is that derivatives with respect to time or anything depending on time are going to go to zero. Our second assumption is that the flow is going to be, or the fluid is going to be, incompressible. This means that the density of the fluid is going to be constant. Third assumption is that the fluid's going to be Newtonian in behavior, and that means that the viscosity is going to be constant as well. So these last two assumptions sort of go together. So we've reduced this to a two-dimensional problem. So we're going to assume the third dimension, guess we'll call that an orthogonal component denoted by this, so to keep track of things. This we're talking about parallel to the flow. This we're talking about perpendicular. And this we're going to be an orthogonal, so coming out of the paper. So we're going to assume that this orthogonal component doesn't matter for essentially anything. And from that, we could assume that the velocity of the fluid in that direction is going to be zero, but we're also going to assume that the only thing that the velocity of the fluid is going to depend on is going to be, well, hold on a sec. What I'm really trying to say is that the fluid's going to be moving strictly along an axis parallel to the plates. So there won't be a component that moves across the plates perpendicular. So we're going to assume that's going to be zero. And you'll see the power in these assumptions when we start applying it to the actual Navier Stokes. So the first thing we could look at for one more assumption that's important is the continuity equation. The continuity equation is going to look like this. Now again, keep in mind that we're working in this coordinate system, so I'm going to use those in the terms of the continuity equation. So don't get too freaked out by these. They'll take a little bit of getting used to since you're used to working in X, Y, and Z. But you'll see the utility, again, of this probably 10 or 15 minutes from now. Okay, so how could we simplify this? Well, we know that we're working under steady state, so this term is time dependent, so it's going to go to zero. The next assumption we could use is that the velocity in the orthogonal direction is going to be zero, and the velocity in the perpendicular direction is going to be zero. So these terms don't matter as well. So we're left with simply the derivative in the parallel direction times the density times the velocity in the parallel direction. It's going to be equal to zero. Okay, so now we could use yet another assumption. Since the density of the fluid is constant, we could pull it out of this derivative, and that is by assumption 2. Now, if you're working with compressible fluids, this isn't valid. You would usually typically have to use the product rule, and then things would get murkier from there. But since we've assumed this to be incompressible, we could pull it out, and then we get this. So, if the derivative of this velocity with respect to itself equals 0, we could tell that this velocity is not a function of its own coordinate. In other words, if you integrate this, you're simply going to get the velocity in the direction parallel to the plates, as it depends on the parallel component, is going to be a constant term. So, if the orthogonal direction doesn't matter, the velocity doesn't depend on the parallel direction, the only thing that's left is that the velocity in the parallel direction is a function of the perpendicular coordinate only. And what that really means is that, say we had a fluid flowing through this kind of arrangement, and say we had something called a velocity profile that looked parabolic like this. So we're assuming the velocity is 0 on both ends. That's called the no-slip boundary condition. And you could tell as you travel perpendicular to the plates, the velocity of the fluid's changing. So that's really what we're saying here. Okay, so what's more interesting to look at is going to be the momentum equations. So if we use the actual Navier Stokes form for our generalized coordinate in the parallel direction, it's going to look like this. And there are a lot of terms, but we'll get through that. So again, don't get freaked out. These aren't 11s. They simply mean parallel. And a lot of these terms will disappear from our assumptions and no longer become a problem. So this you can find in most fluid mechanics textbooks and on the internet. So I encourage you to go look up this equation because it's very useful. Okay, and lastly, we have this gravitational term in the parallel direction. Alright, so that's a lot of terms. Keep in mind that the only reason we're allowed to have this mu out front here, and this written this way, is because we've assumed that we're working with a Newtonian fluid. If you work with non-Newtonian fluids, you're going to have to actually use the Navier Stokes equation with the stress terms in there. Again, we're not going to have to do that here. So let's work through these terms again from these assumptions. So again, we're assuming steady state. This term's time dependent. We know it's going to go to 0. We also know we've assumed the orthogonal velocity and the perpendicular velocity to be 0. So we know that these two terms are going to go to 0 as well. Here we're taking the derivative of the velocity in the parallel direction with respect to the parallel coordinate, but we've assumed that velocity is only dependent on the perpendicular component. So by assumption 6, this is going to go to 0 as well. Over here we have the same sort of thing. Again, the only thing that the velocity in the parallel direction depends on is the perpendicular component. So for the same reason, these two are going to go to 0. So what we're left is, I'm going to move this to the other side. dP, the pressure dependence in the parallel direction, minus the gravity term in the parallel direction. It's going to be equal to the viscosity times the velocity in the parallel direction, the derivative with respect to the perpendicular direction. Okay, and this we're actually going to be able to solve, well, sort of explicitly. So I'm going to do that quickly, I guess, here. So nothing over here depends on the perpendicular component, so we could simply integrate this. Should probably move this over first. So 1 over mu dp d parallel minus rho g parallel d squared velocity in the parallel versus derivative with respect to perpendicular. So if we integrate this once, we simply get a perpendicular component here. We get a constant term, C1, and that. If we take the integral again, we're going to get this squared over 2 mu, same term here. This gains a perpendicular component, and we have a second constant. So that's the velocity of the parallel as it depends on the perpendicular component. So we're going to come back to this in a little bit. But there's still some work we could do with our other momentum equation. So we're going to look at that quickly. Okay, so if we examine the momentum in the perpendicular direction, the same Navier Stokes equation, what we get is this. Again, it takes a little bit of time to write this down, but you should get, practice doing it yourself. And my handwriting isn't the greatest either. That doesn't help. dv perp orthogonal d perp mu v perp, and lastly, well, not lastly, there's also gravity in the perpendicular direction. Oh, I'm sorry if I cut that off, but it's back. So again, how do we simplify this? Well, we know by our steady state assumption that this is time independent, so that's going to vanish. We also know, remember, that perpendicular velocity equals 0. So then, by this assumption, these three terms have perpendicular velocity. These three terms have perpendicular velocity. The only term that's left is the gravitational one and the pressure one. So I'm going to move this over to the other side. We have dp, d perp, minus, well, I'll just set it equal to rho g perp. Okay. This is pretty easy to integrate. There's not a lot going on there. We know that pressure, the perpendicular direction, is going to be rho g perp times the perpendicular component, and we have yet another constant. We'll call this one C3. Okay, so this is going to come back, and this is going to be useful as well. So at this point, we've done most of the hard work as far as the physics goes. There's one other thing that we should get cleared away. So we have our coordinate system oriented like this, and we have gravity going downward like this. So if we're going to have our coordinate system pointing straight up, well, again, we have an angle here, theta. If we're going to rotate that coordinate system, so as normal, the gravity vector would come down like this, and what we get is, I believe it would just be here. So our gravity vector is going to look like negative sine theta this way, and negative cos theta this way, because remember it points leftward and downward, and we're looking at the trigonometry as it appears here. Okay, so we have most of the things we need. So this actually tells us the formulas that we're going to be using. So let's actually solve problems now that we've found this. So I'm going to simply bring those out over here. Again, this is simply the velocity parallel depends on perp that we just found first, from momentum in the parallel direction. This is simply that derivative that we found in an intermediate step. You'll see how this is important, and this is what we found from the perpendicular momentum equation. Okay? So how could we actually apply these to solving problems? So let's think about probably the simplest problem that we could have. So completely horizontal coordinate system, the fluid flowing in this direction. Again, we got L this way, and now we got gravity going down like this. And what else do we have? Let's actually use a standard coordinate system this time. So we have, say, X in this direction, Y in this direction, and Z is coming out, but Z also doesn't matter. So how can we solve for the velocity profile velocity, V max, V average, all these things? Alright, well, now I need to look at the initial conditions and the boundary conditions of what we have here. So the first assumption we're going to apply is the no slip boundary condition that I mentioned before. That simply means that if we have a fluid going through here, the velocity at either of these edges will be 0. So the velocity in the parallel direction, which is equal to Vx in this case, will be 0 when y equals 0 and y equals L. Because remember, y is going to be our perpendicular component, so at y equals 0 and at y equals L. Okay, what else do we know? We know that the gravitational component in the parallel direction, which we said before was rho g sine theta. Well, since theta is 0, this term is going to go to 0. We know that the gravitational in the perpendicular direction, which we had as this, as theta goes to 0, is simply going to go to rho g. Okay, so then all we need to do is apply these boundary conditions. First, I'm going to rewrite the velocity with our new coordinates. So we have y squared 1 over 2 times the velocity. Remember that this term is going to be 0, and this term is simply going to be, sorry, this term doesn't go to 0, this term will go to 0. dp dx. And we still have that c1 times y and c2. So if we apply our boundary condition 7, Vx of 0 equals 0, these both go, and we find that c2 equals 0. If we apply 8, see that Vx of L is going to be, well, it's going to be sort of a mess. Guess there's nothing to do with it. Well, I'm going to quickly call this quantity A, so we have L squared A plus C1 L equals 0. So then C1 equals negative L squared a over L equals negative LA. Where again, A is just, we've grouped this together because I didn't want to spend 20 minutes writing it out. So we found both of these constants. So we know our velocity is going to be Vx, depends on y. Call that A again. L squared, negative LAY. And that's it. So we know it's going to be, well, you know this form is simply, I guess, parabolic with a negative term that's linear. Okay. And just in case you cared about our pressure in the y direction, we see that it's going to be negative rho g, well, times this, rho gy. And what else can we tell? Well, we can tell that, hold on a second, I want to check something. Oh, well, we can tell that it's going to be there, but it doesn't actually affect anything on our velocity profile for the other direction. At least I don't believe. I'm going to put a star here and check that later. But what are we going to do for, again, these things that we're looking for? Well, we know that if we were looking at this, just as a regular function, you know, that would pretty much look like this. And unfortunately, we're looking at this sideways, so our velocity profile is going to be of this form. Okay? And if you wanted to find Vmax, what you do is you take the derivative of this, find the zero of that, and that'll tell you the y value. That'll maximize it. You could also tell it's simply going to be L over 2 through here. If you wanted to find V average, that would simply be this integral. So you're looking at it as it depends on the cross section over the area. Okay? Similar things for if you wanted to find the flow. These are just kind of general. Again, I'm not going to do them for the other problems because the integrals get pretty messy and they're not very illuminating. Okay, so what about the situation where we have perhaps something a little more complicated? So say we're looking at a vertical setup like this. Say this wall is stationary, but this wall is moving upward. We have fluid moving down the channel. And again, say this distance is L. Let's define our coordinate system again. Call this the x direction, and this the y direction. Okay, so what initial conditions and boundary conditions do we have for this to be true? Again, we're applying no slip. So, again, it's going to be, well, in this case, velocity parallel to the direction of flow is going to be Vy in this case. So Vy will equal 0 when x equals 0. So when we're along this wall, we apply the no-slip boundary condition and the velocity is going to be 0 there. And Vy will equal v, the upward velocity of this wall, when x is all the way across here. The other two things we can figure out are those gravitational terms. So gravity in the y direction is simply going to be negative rho g and gravity in the x direction is going to be 0. Alright, so we're going to apply these equations once again. So this time we're looking at Vy, as it depends on x, because again, y is parallel to the flow, x is perpendicular, and that's going to be equal to x squared 1 over 2 mu dp dy. This time we have the negative rho g, so it's negative rho g. So we're actually going to add it this time. Okay. We're going to have, again, C1x and C2. Okay. So let's first apply 7 to make our life easier. Both these terms vanish. C2 is 0 once again. And over here, we know that's going to be V, and that's going to be equal to L squared 1 over 2 mu dp dy plus rho g plus C1L. And you could solve this for C1. And this time what you're going to get is V over L minus L over 2 mu dp dy plus rho g. So your final velocity is going to be x squared 1 over 2 mu, that term in there, plus V over L minus L over 2 mu, again that term in there, times x. What you really care about is this is the form of ax squared plus bx. Okay? And again, if you examine the pressure, what you're going to find is that it's simply going to be rho gx times x plus C3. But we already see here this is going to be 0, so C3, well, we don't actually have a boundary condition for our pressure. We can also tell that it's just not going to matter. We'll actually do a problem where the pressure term matters, but here it doesn't affect anything in here particularly. So how do we figure out the velocity profile of this? Well, we know that along this wall, it's going to want to move upwards. Here, it's going to be 0, but a moment afterwards, gravity is going to be pulling it down. So we know that velocity will be down here and up here. Now there's something you probably know called the intermediate value theorem from Calc 1. Well, we know if velocity is going from negative to positive, there needs to be some point along here where the velocity had to be 0. So we're just going to make a line there and say this is a 0 line. We're going to say that, okay, we know the velocity was 0 initially, but we know it goes down. Eventually, it must have crossed back up to here. So the velocity is going to look like this. Because remember, towards this wall, it's going to move up the wall as the wall moves up. And here it's going to be 0, but instantly afterwards, gravity is going to pull it down. We know there's got to be some sort of 0 value along here because of the intermediate value theorem. Okay. So hopefully that made sense. Let's look at yet another condition. So say we have a similar sort of circumstance where again we have that vertical setup here. We have this left wall moving up with a velocity v, and we're going to call this air. So there's no hard wall here, it's simply air. So how does this change our initial conditions and our boundary conditions? Well, this one's probably still close to okay. we know that Vy is going to be V, when x is 0. We also know, well, that's pretty much all we can tell about the velocity. So another thing we could tell is something called the stress in the y direction. So this is a shear stress, so it's going to be acting in the y direction. Again, y, x, in a plane perpendicular to x. So it's kind of like you have shear coming out along here. So it's going to be pointing along here, but that's why you have the x. The y is because it is along here. I hope that sort of made sense. We know this is going to be 0 at x equals L, because again, there's no longer a wall here, so there's nothing that's actually applying a shear stress. So that's why it's going to be 0. So this formula you should know as well. The stress as it looks in this form is equal to dVi dj plus dVj di. Okay, so